Hello, and this time we're looking at using the binomial distribution in a statistical question and a statistical context. I've got a question here that you asked to go through, so let's have a look. First question, write down the conditions under which the binomial distribution may be a suitable model for use in statistical work. Well, there's 4 marks here, so I'm assuming we're wanting 4 things. First thing that comes to mind is that you need 2 outcomes, exactly 2 outcomes. So a heads tails situation or a win-lose situation. Obviously, you can't use binomial if there's more than 2 possible outcomes. On that note, those outcomes have to be the same probability each time. So if it's a game, the chance of winning the first time and the chance of winning the 10th time, they've got to be the same. It can't be that, sometimes the probability of winning is greater or less. Every probability, every trial that you do, the probability must be the same. And the third thing I'd say on that is that each time you do the game, it has to be completely independent. The probability has to be independent each time. The outcomes have to be independent, which means that doesn't matter if you win or lose the first time. If you win the mega jackpot prize the first time, then you should have the same probability of winning the mega jackpot the second time. Now, obviously, there's only 2 outcomes. So in this scenario, you either win the mega jackpot or you don't. But the fact that you win it the first time means the second time you have to have the same chance of winning. It can't be like, oh, well, you've won it already now, so there's no, much less chance of winning it. That must not be the case. It must be completely independent, so that what happens the first time does not affect in any way what happens the second time. And like I've already said, part 2, that means the probabilities also have to be the same every time. But it might not just be that they would change if it was if the probabilities were dependent, they would change. But even if they're independent, they might be different for different trials. But we've already covered that. That must not be the case. And the final thing is there must be a set number of times you're running the experiment or playing the game, whatever it might be, a fixed number of trials, let's call it, in that you must be playing the game 5 times or doing the test 8 times. You can't have, oh, so and so is just going to play the game until they win. That isn't going to work for the binomial distribution, because the number of times you trial it will affect what the probabilities are because of the multiplicity. If you remember, if you've looked at binomial distribution before, you know that when you expand the bracket, you get a coefficient on each one, and that coefficient comes from Pascal's triangle. And the bigger that value is, the bigger those coefficients are, and it changes the amount that you're raising each probability to as power. So all of that changes, and it depends on the number of trials, which is obviously the n in the bracket, the power outside the bracket. And if that isn't fixed, then you can't do any of the processing. Okay, so those are the 4 things that I think they are looking for in part A. Oh dear, just lost the top of the question. There it is. Okay, so let's look at part B and let's see what that's about. A 6-sided die is biased. Okay, so some of the outcomes are going to be more or less likely than the others. When the die is thrown, the number 5 is twice as likely to appear as any other number. All the other faces are equally likely to appear. Okay, and the die is rolled repeatedly. So we can definitely make this a binomial, which is pretty obvious because it's a binomial question, so it's going to be binomial in part B as well. Find the probability that the first 5 will occur on the 6th throw. Wow, okay, so we want the probability that the first 5 will occur on the 6th throw. Now, we've not been told, unless I've misread it, how many times we've thrown it, but each question has that built into the question. So the question here, we only care about the first 6 throws, because I want to get not a 5 for 5 throws and then get a 5. And whatever I get after that, it doesn't matter. So we can set this to be a question with exactly 6 throws. But also, we don't need to actually do this as a binomial question. We can just think about this logically. The first 5 will occur on the 6th throw. That means I'm going to have 5 throws that are not a 5, and then I will have a 5. Okay, so that's what we're going to have. These 6 throws, I want not a 5 for all of these, and then I do want a 5 on this one. And there's only one way to do that, which is to have not a 5 all these times and a 5 here. If the 5 is twice as likely as any other number, then instead of being all out of 6, we can just say this is all out of 7. Yes, because the 5 is taking 2 portions of the probability. So the probability of a 5 is going to be 2/7, which means the probability of not getting a 5 all of the other times is going to be 5/7. And this one's 5/7, and this one's 5/7, because every time the probabilities are and the outcomes are independent, so it's always 5/7, except for the last time I do want a 5 to occur this time, 2/7. And I'm just going to multiply all of that together. Now obviously for the calculator it'll be much easier to do all of that, 5/7, do it as a power, 5/7 to the power of 5, and then times 2/7. Do that on the calculator and we should get the probability. Okay, and then the question part 2, in the first 8 throws there will be exactly 3 5s. So this time I think we will use binomial, because in this one we've got a set number of throws, 8, and we want exactly 3 5s. We don't care how they're ordered, whether the first 3 are 5s and then not, or if they're spaced out. So this is a binomial question. Now if we were going to expand the binomial, if you remember, you have the probability of the first thing, so let's have P, we'll say as getting a 5. So P is getting a 5. And we want 3 5s, so that's going to be to the power of 3. And then we have this times Q, and Q is 1 minus P. That's what Q equals. It's the probability of not getting a 5, and that is going to be to the power of 5. And that's because we've got 8 throws. The 2 powers have to add up to the number of throws, which is 8. And then we've got the probability, sorry, not the multiplicity in front, which is found with NCR. Okay, so NCR, and there's a button on the calculator for that. And in this case, the N is going to be 8, and then the C, and then the R value can be either one of these values. Okay, so we could put 3 in there, not a problem. It doesn't matter which one you use, because if you remember, Pascal's triangle is symmetrical, so we should get the same answer either way. But let's have a little look, just check that I've got that right. So 8 NCR 3 gives me 56, and 8 NCR 5, can't remember what it was now, yes, also gives me 56. Okay, and then, so we know that's 56. The probability of this, we've said, is 2/7, so it's 2/7 cubed. What was that? 56. And this is 5/7 to the power of 5. And you can put all that in your calculator, and the answer it will give you is going to be what it's asked for, the probability of getting exactly 3 5s. There's your 3 5s, there's 5 that aren't 3, and there's 56 different permutations, combinations I should say, of how you could achieve that. But there is another way of doing it. You could just use your calculator. You need to say what you're doing, so you need to say what your values are going to be. that you're going to just shove into your calculator. So you probably want to write down that x equals, wait, no, n equals 8, x equals 3, because there's 3 outcomes that we want, and the probability of achieving that outcome is 2/7. So I think you should write that down. You need to say that so the examiners know you haven't just made it up. And then on your calculator, if you remember, it's the distributions, which I think is 7. Yeah, it is 7. And binomial, okay, and it's the binomial PD. Remember, binomial CD is the cumulative distribution, and you can let me know what PD stands for. If you know what the P is, you can write that down in the comments. Precise distribution, maybe? I don't know. But anyway, it's PD that we want if we want to know an exact value, the probability of this thing happening rather than a, up to and including. So click on this one. We want to write it in as a variable, not as a list. Click number 2, and we're going to type in the values. I did do it in the wrong order, never mind. So the x value, there's 3 outcomes that we want, a total of 8 trials, and the probability, you can write it in as a fraction, that's absolutely fine, 2/7, and it will then convert that for you, and it then just tells us what the value is, and we write it down. It's that straightforward, especially if you've got your calculator. Hopefully that was helpful. If there's anything you still don't understand, then let me know in the comments below. Thanks very much, and see you next time.